So considering the observations that they made, they came up with one of their own architecture and model, that is Neuro Symbolic Dynamic Reasoning. Now this consists of 4 parts, which is video frame parser, dynamics predictor, question parser, and program executor. I'll be going deep in each of them, and at the end there will be an example explaining the total input and output. So first we come to the video frame parser. So this is responsible as one of the key observations they made, that object-centric proposal is required. So this is responsible for getting the object detection, and it does the scene re-rendering, which outputs the mask of the object, it outputs the attributes, and also the labels of the object. Now this is trained on randomly sampled 4,000 video frames out of the entire data set. Now, the next part is the neural dynamics predictor. Now, this is one of the novel proposals that they have made. This is basically a crop net. Now, propagation network is one of the extension to the interaction network that was proposed by DeepMind in 2016. Now, this is a graph network where the objects are the vertices and the edges actually denote the relations between each object. Here, the object is represented by a state and their attributes, and the relations are represented by the objects that are receiver and sender, as well as the attribute. Here the attribute to the relation is only one, that is collision. But whereas in the PropNet, in the original paper, they have discussed like planning the dynamics for spring or something like Newton's cradle, where they can also add the attribute of spring tension, something different. Now, what is the state of the object? Can you go back. Yeah. The state of the object is actually represented by the image, the mask patch, and the position of the mask in the entire image. Now, this is important because the position of the object will be the core part where they will understand how the object-centric proposal will help in the counterfactual parts. So now basically this is a graph network. Now here they are not using the state of the graph as is. They are using an encoder and decoder over here. So here, as you can see, there is encoder for objects as well as the relations. Now these encoders are initialized as convolutional neural networks. Now how this thing actually works is that for this is a planner which is trying to find out what is the future trajectory of the objects. So it is trying to go from t equals t to t equals t plus 1. If we take this example that it wants to go to t from t, it wants to predict at t plus 1, there are a number of propagation steps that you are supposed to include in it. Now this is a graph network where it relies on the message passing and the information diffusion between each of them. So the number of propagation steps intuitively are saying that how many times you want to diffuse to stabilize your equations so that you will reach the next time step. So here the N will go from 1 to capital N, while T will be going from, T is the simulation step, that will be going from T to T plus 1. Each time there is, I didn't mention this. Here the H represents the effect of object I, the E represents the effect of relation that is happening. And as there are encoders, there are also decoders, as well as there are propagators that you can see here, FO and F1. Next slide. So this is the algorithm that goes into the picture. So here initially the effects due to all objects are initialized as 0. At each step, the FR and FO, these are nothing but MLPs with 1 layer and 100 dimensions. Now these take into the consideration the previous H as well as E, but you can notice that C is not dependent on L at all, because we are trying to go from T to T equals T to T plus 1. There is no difference between, there is no point where we are changing the object. They are just doing it at the latent representation in graph. So the C doesn't depend on L. So and at the end, at L equals capital L, you will reach to the point where you will use the decoder to get back from this latent representation to the original state. Go ahead. So that is basically how the dynamics predictor works. Now, the next part is the question parser. Since this is a visual question answering format, you need to understand that how you are supposed to take the text. So they are using bidirectional LSTM over here, where the encoder every time they are taking out the self state as well as the hidden state, and for the forward as well as the backward pass. And go ahead. And at the same time, decoder is also using those representations which are merged, and then the final output that comes from the question parser are the program tokens. Now, the output from the question parser as well as the dynamics predictor will be consumed by the program executor. And this is how they are actually using disjoint representations from both of them and merging them. Now, this is initialized at two hidden layers at which are 256 units and 300 dimension word embedding. And one important thing to note over here is that there are open-ended questions as well as multiple choice questions. So for open-ended questions, only the question goes through the network of question parser. But for multiple choice, each choice along with the question goes with it. And there is in the program executor, there is a part where they will be merging that and say give an output of yes or no. So the program executor is basically a collection of different modules which can be categorized into input, filter, or output. Input, now the way these modules will be represented, will be sequentially laid down, will depend on the output of the question parser. And the input modules inside those modules will be querying the output from the dynamics predictor. The filter output will be responsible. Filter output will be responsible for performing the logic operations, and the output will be responsible for giving it in the right format, whether it's a yes/no question or whether it's a open-ended question, descriptive one. Next. So here is an example that you can see. So here a red sphere is coming into the picture, and it's hitting a cyan cylinder, and at the same time it's hitting another cylinder. So the question, when you are laying this question over here, it comes out with a program that gives this format and this sequence of modules. Because of this sequence, then it will be querying the output from the dynamics predictor, and it gives out this answer. So this is how the entire representation from visual as well as the text is considered and giving an output. Next. So as far as the results are concerned, one thing, if you remember, Ashish had mentioned that the original MAC paper was giving a result of per questions, which was in tens. It was 12, 14, 12, something like that. And if you can see the improvement in explanatory, predictive, and counterfactual, here there is a massive boost from how the NHDR is performing. So from the NHDR part, we understand that they are able to predict. You are able to predict that, okay, now this is a T, and what will be there 5 time steps ahead. You can understand that because of the propnet. But how are they actually considering the counterfactual part? So as you remember that in the graph, each vertex will be responsible for representing an object. Now, when you want to say that what would happen if the red cylinder is not there, you have to remove that vertex from that graph. And the planner that has already learned, the dynamics planner that has already learned it, will give you an output where the vertex won't be there. So as far as the results are concerned, they also come up with another variant of the goal, which is no event. Now, what is different in this is that in the original one, they are actually, when the collision happens, they are actually changing the attribute of relation to 1 or 0 based on the collision. But here they are calculating that based on the direction and the velocity of the objects. So the results provided by that are provided here, the question parser is trained with 1,000 programs. So that gives you this is the accuracy based on that. So limitations and future work. So here authors specifically mention a need to decrease the supervision that's required. According to them, there is a very large amount of supervision that is required, because if you take this example into a real life, then it might not be that practical. If you say that I want to model 2 people, they are shaking hands, you want to find the explanatory part, if both of them are wearing blue t-shirt, then how is that model going to understand? The data set has also particularly avoided collisions between the same objects. This is one point that is important to understand, that they are avoiding that, so that is one point. And another part is they understand that there is a fall or loss of performance as they go for multiple future steps, and they say that dynamics planner need to be improved. Another point to be noted over here is there is a paper for COMP5, which states for Compositional Physics Planner. So they also mentioned that CLEVRER NHDR doesn't take into consideration the interactional dynamics between objects. So for example, the objects used over here are pretty simple with no eccentric attributes. But they mentioned what would happen if you are using two magnets. So two objects can have different behavior with each other based on attraction or repulsion. How is the probenet going to understand that? So these are few of the limitations and future work that the authors propose. And summarizing it, I would be saying that NHDR has been one of the novel work and pioneering work for laying down the causal part in the visual question answering, which gave a big boost, and it is responsible for actually laying the foundation for multiple future work, and a lot of few further research has happened. Thank you.